All right, looking at this particular problem, we're looking at a hypothesis test for the difference in means. I'll let you pause and read the context on your own time now if you'd like. But the gist of this is that we want to test for a difference in means between two drugs. We have a current drug, and then we have a new drug that they want to test cholesterol reduction in. Okay. The important thing in this example is that they're not testing that the difference is 0. They're testing that the difference is 10. So read up here, if the data provide convincing evidence that the mean cholesterol reduction with the new drug is more than 10 milligrams per deciliter of blood, greater than with the current drug, the company will begin the expensive process of mass producing the new drug. So in other words, they need to see a decent difference between these two things in order to spend the money and to start producing this new drug. So that's the big difference here. Our process stays the same. We're going to start with the state. So that statement looks like this. So we're going to tell them we're going to test here at the alpha equal 0.05 level to check for more than a 10 milligram per deciliter difference between the current drug and the new drug. So a little bit general there. We'll get a little more specific under the do step. Next thing we got to do are our hypotheses. So got our null hypothesis, which looks like this. Got the mean cholesterol reduction of the new drug minus the mean cholesterol drug or cholesterol reduction of the current drug is equal to 10. And then our alternative hypothesis is that the difference in the means is bigger than 10. So there's our null and our alternative hypotheses. Next thing we want to do is make sure that we specify what this new notation means. And that looks like this. So as we just described, mu sub n is the population mean, the true mean reduction in cholesterol in the new drug. Mu sub c is the true mean reduction in cholesterol in the current drug. So we can now move on, check our conditions under our plan step. Those conditions look like this. First thing we want to look at is, are they randomly selected for the sample? So we've got 14 subjects assigned randomly to the current drug, 15 subjects randomly assigned to the new drug, and this is a completely randomized experiment. And so so they are randomly assigned. And then the second one, completely randomized design or experiment, allows us to say, hey, we don't need to check this less than 10% because we don't have a sample of a population. We're just performing an experiment. Before that or after that, we're going to check to see if our sample sizes are bigger than 30, so that we can so that we have an approximately normal sampling distribution of differences here. Our sample sizes are not bigger than 30 in this case, but we have this nice little explanation here. So if we don't have big enough sample sizes, quote unquote, we can check the graphs to for any outliers or strong skewness. Here we don't have to check it. No outliers or strong skewness tells us that our sampling distribution of differences is going to be approximately normal. So we're good to go. Moving on now to the do step. And here's what we need to specify. We need to talk about the type of test and then the specifics of that test. So that looks like this. So we're going to run a two-sample t-test for differences in mean. So a couple of things. Number one, if we're going to run a t-test, we've got to know the degrees of freedom. Okay, so our degrees of freedom is going to be, we're going to take the smaller sample, which is 14 subjects, and subtract one from that. So we're going to have degrees of freedom of 13. And then the next thing is I've got to calculate my t statistic. And this is where it's maybe a little bit different. We usually use our calculator to do these two things. But this is where the difference comes in this problem, because our null hypothesis is not that there is no difference between the two means. Our null hypothesis is that there is a difference of 10 between the two means. And so that changes our t statistic. So when we go to calculate our t statistic, we want to take the difference in our sample means, which looks like this. 68.7 minus 54.1. Notice I kind of switched the order. So this is the This is the mean for the new drug, mean cholesterol reduction in the new drug. This is a mean cholesterol reduction in the old drug. And I switched them just so we could have a positive result here. And then we're going to subtract the difference in population means, which we've assumed to be 10. So that's what our numerator looks like. Our denominator then is the standard error of this sampling distribution. So that's going to look like this. We've got the square root of, so this is the sample standard deviation squared of the new drug, and it's divided by however many there were for the new drug. So we had 15 subjects that were assigned to the new drug, and we'll do the same for the current drug. So we got that inserted here, and then plug this stuff into your calculator very carefully. And when you simplify, you should get something that looks like this. So there is our t statistic. We've got 13 degrees of freedom, so we know that that our t distribution is going to be based on this number of degrees of freedom. So we go over to the calculator and we calculate the probability of getting this thing, this t statistic, on this distribution, and that will give us our p-value. So just to kind of get a picture of what's going on here, on this t distribution, 13 degrees of freedom, it's going to be a little flatter than a normal distribution. Here's our center, and essentially we found this t statistic of about right here. And what we want to know is what's the probability of getting this thing or more extreme. So we're calculating with TCDF what that probability is going to be. So let's head over to the calculator, plug our info in, and see what probability or p-value that this is going to have. So we go over to statistics, distributions. We want our TCDF. The lower bound is going to be our z-score for that. Sorry, t-score for that, which was 0.9816. The upper bound is going to be infinity or something really, really big. So we'll just plug in really big number, and then degrees of freedom is going to define how flat or how well it resembles that normal curve. So we've got 13 degrees of freedom here, and you hit OK, and it's going to spit out that probability. So this is our p-value, 0.172106. Because this is a one-tailed test, that's all of the p-value. We don't have to compare it against half of the alpha or double it to compare it against all of the alpha. We just look at this p-value and compare it to alpha, and we're good to go. So let's go back to conclude this thing. So you can see under our do step, I've got the three main ingredients here. I told you what test, and once I specify that test, the t-test for differences in the mean, I need to know the degrees of freedom, I need to know my t statistic, and I need to know the p-value once I run the test. So we can go ahead and make our conclusion. Remember, this is a one-tailed test at the alpha equal 0.05 level. I've got a relatively high p-value compared to that. So in my conclusion, this is what it looks like. So first part of your conclusion, you're going to take your p-value, you're going to compare it to the alpha level, and you're going to make a decision. So with a p-value of 0.172, we failed to reject H naught at the alpha equal 0.05 level and conclude. And this is where you give your context that we conclude that there is insufficient evidence of a mean cholesterol reduction difference of more than 10 milligrams per deciliter. You can add a little bit onto this if you want, and essentially say that the company should not start the process of mass producing the new drug.